All right, welcome everybody. Let us have a discussion of section 11.9, representation of functions as power series. So there may not be too many exercises here, but hopefully we can go through these. So the radius convergence of this power series is 7. What's the radius convergence of this power series? Ooh, that's the derivative of that power series. And frankly, one of the main consequences of this section is that under differentiation, power series radius of convergence is preserved. And so, yeah, the radius of convergence remains the same. Yeah, that's the answer. The radius of convergence remains the same when differentiated. This is part of what allows us to extend Taylor's identity for for Taylor polynomials to Taylor series. And so that's the idea that nails down that theory. Right, find a power series representation for this function. Okay, so here's the idea. The idea is this function looks like a over 1 minus r from a geometric series. So a is 7. We know the first number in this series is 7. And r is, because 1 minus r goes downstairs, this is from a geometric series, the common ratio is x squared. So how do you get to each next number? You multiply by x squared. So the first number is 7. The next number is 7x squared. The next number is 7x to the 4th. The next number is 7x to the 6th, and so on. So how are we going to write that? We're going to write that as what? 7x to the 2n, because, right, for n equals 0, you just get 7. For n equals 1, you'll get 7x squared. For n equals 2, you'll get 7x to the 4th, and so on. So 7x to the 2n is what results here. And yeah, determine the interval of convergence. Well, we're going to have to go through a ratio test for that and deduce the result at the various endpoints as well. So we're going to have to take that expression 7x to the 2n and run a ratio test. So of course the 7's would cancel. When you set that less than 1, I believe you'll get absolute value of x squared is less than 1. And then take the square root of both sides, you get absolute value of x is less than 1. And so you'll have an interval of convergence of 1. If you try testing the endpoints, I believe because we are a geometric series here, we would fail at both of the endpoints. The geometric series, when you have a geometric series, both endpoints fail, right? Because when the absolute value of r is 1, you diverge. So I think that's the way that's going to play out. So I think we'll get we'll basically be from -1 to 1, including neither endpoint. Find a power series representation for this function. Now, to do this, we are going to have to look up I believe we're going to have to look up the power series for tan inverse. So there is a power series representation for tan inverse. We might have to look that up in the textbook. Once we get the power series for tan inverse, we're going to replace x with x cubed, because that's going to be tan inverse of x cubed. And then we're going to take what results and multiply everything by x squared. So you can think of the x squared sort of being multiplied on the outside, and then the x replaced with x cubed in the tan inverse formula. So that's going to require us looking up the formula and going through it that way. Okay, evaluate this indefinite integral as a power series. So you see here, the first thing we're going to do is view this of the form a over 1 minus r. R here is t to the 8th. A here is t. So this as a power series is t plus t to the 9th plus t to the 17th. We're multiplying by t to the 8th to get to every next term. And yeah, so when you view that as a power series, what? You're going to have t to the 8n plus 1 as the expression. So sum from n equals 0 to infinity of t to the 8n plus 1. I'm sure they'll walk you through this process. Once you get that, then you can run the ratio test to determine the interval of convergence. The interval of convergence is positive, which means you can integrate or differentiate. Yeah, then if you integrate the expression, you'll get a power series expression. So you essentially run the you'll just have to do the power rule on each of the terms, and then yeah, that's that. And The radius of convergence will pop out to be whatever it is. I believe in this case the radius of convergence will be 1 because your power series is just some t to the 8n plus 1. I think that will come out to be a radius of convergence of 1, but don't quote me on that. Okay, this is similar to the previous example, but now with the ln function. So you'll have to take the power series representation of ln x, and then replace x with 1 plus x, and then multiply every term by an x squared. And so you might have an x squared within your expression, not sure how the power series of ln 1 plus x is. Well, I guess ultimately that would probably give you like x to the n plus 2 or something, because you'd have to add 2 powers of x to your expression. And then yeah, you're gonna I guess compute the radius of convergence. I think the radius of convergence is 1 for the ln function. Could be wrong, but that x squared could have an effect there. I'm not exactly sure. But then now once you get this power series, you see you can just use the power rule to integrate, which is pretty badass, because yeah, there'd be pretty much no way to integrate this otherwise. This is a nasty one. Maybe we could use integration by parts, but boy, it would be that would be rough. Okay, let's go on to the next one. Oh, okay, so see, this one's probably easier than some of the previous ones, because here you're going to take the expression for tan inverse of x, and then take whatever that expression is, and then just divide x from it. So dividing x from it is essentially going to reduce every x power by 1, and then you're going to integrate, which is actually going to increase the power by 1, but use the power rule. So you're going to have to divide by, increase the exponent by 1, divide by the exponent. So take that term by term within the expression. And yeah, I'm not sure what the radius of convergence is for the tan inverse function. That will be something you'll have to determine using the ratio test. Find the power expansion of this. Right, so view this as 1 over 1 minus x to the 6th. So this is almost like a geometric series expression, a over 1 minus r, but the a is 1. Like take the dx and just push it to the right. 1 over this. And downstairs, view it as 1 minus negative x to the 6th. So negative x to the 6th is your common ratio. The first term is 1. The next term is minus x to the 6th. The next term is plus x to the 12th. The next term is minus x to the 18th. So thinking about that within a series expression, you would have sum n equals 0 to infinity of x to the 6n with a factor of minus 1 to the n in front, because every other term was negative, right? It's an alternating series. So you have minus 1 to the n, x 6 to the n, and then what do? You integrate that. You integrate term by term, but once you have an expression for the power series, integrating term by term is just taking that symbolic form that's in the summation and integrating it, which is one of the reasons why we like power series, because once you have this expression written in sigma notation, then whenever you integrate, it's like about as straightforward as you could possibly imagine to go through that integration. It's just the power rule, right? Power series abide by the power rule whenever you are integrating or differentiating, and as seen in that top true-false example, you don't disrupt the radius of convergence whenever you differentiate or integrate, which is one of the benefits. So, all right, that rounds out the 11.9 exercises, and well, that's that.